Phase relationships of current and voltages. In a series circuit, the current is the same through both the resistor and the capacitor. The resistor voltage is in phase with the current, and the capacitor voltage lags the current by 90 degrees. There is therefore a phase difference of 90 degrees between the resistor voltage V sub R and the capacitor voltage V sub C. If we look at this sinusoidally, it becomes more apparent. So the phase relationships of current and voltages, the current leads the voltage across the capacitor by 90 degrees. So here we can see the current, the gray line, and we can see the capacitor voltage, and you can see we have 90 degrees of shift that occurs. The amplitudes in this case are arbitrary. So the phase relationship of voltages and currents then can be displayed sinusoidally as well. You can see the voltage across the resistor is tracking that of the current. Kirchhoffs Voltage Law says that the sum of the voltage drops must equal the applied source voltage. Since the voltage across the resistor and the voltage across the capacitor are not in phase with each other, they must be added as phasor quantities, with the voltage across the capacitor lagging that of the resistor by 90 degrees. So the idea behind this is we can only add the real parts to the real parts, the resistance, and the imaginary parts, the reactance, to the reactance. Okay, so Kirchhoffs voltage law, as we learned it for DC, does not track exactly. So in a phase relationship diagram here, we can see by using the phasors that we have the voltage across the resistor and that of that capacitor out of phase or lagging by 90 degrees. So if we take a look at just the voltages, so we've got the voltage across the resistor, we've got the source, which is actually the resultant in this case, and the voltage across the capacitor, 90 degrees. So if we put them together as the voltage drops in phasor form, the source voltage is equal to the voltage across the resistor minus the J voltage across the capacitor. So you can see we can't add them directly. We can only sum them vectorially. So if we convert these then to polar coordinates, you can see again by applying the Pythagorean theorem, v squared r plus v squared c added together, take the square root, and then taking the negative inverse tangent of v sub c by v sub r gives us then our polar representation for a phasor quantity of these values. Since the resistor voltage and the current are in phase, in this case theta also represents the phase angle between the source and the current. And so if we look at this diagram, we can see we have the current I totally in phase with the voltage across the resistor, but lagging by 90 degrees across the capacitor. Capacitive reactance varies inversely with frequency. So when the capacitive reactance X sub C increases, the entire term under the square root sign increases, and thus the magnitude of the total impedance also increases. So this is really just telling us, because of that capacitor, we've got some frequency dependence going on, and that's frequency, as we vary it, is going to change the overall value of the impedance. When X sub C then decreases, the entire term under the square root sign decreases, and thus the magnitude of the total impedance also decreases. So in an RC circuit, the impedance Z is inversely dependent on the frequency. In this pictorial, all we're doing here is we've connected some ammeters and some voltmeters across the resistor and the capacitor, and looking at the representation as we vary the frequency on our frequency device here. Okay, so this is our frequency generator. As the frequency is increased, the current and the voltage drop across the resistor and capacitor decreases. So we're increasing the frequency, the current increases, the voltage drop across the resistor increases, the voltage drop across the capacitor decreases. So if we decrease the frequency, as we see on the frequency generator, the current decreases. That's the total current. The current through the voltage across the resistor decreases, but the capacitor voltage drop increases. So this is an illustration of how the variation of impedance affects the voltages and currents as the source frequency is varied. The source frequency then is held at a constant amplitude, so that doesn't change. So in this case, in the pictorial, what we're seeing is how the impedance and X sub C, the reactance, change with the frequency. So by watching the two meters, the current ammeter and the meter on the right, V sub Z, by watching these two meters, you can see what Z is doing. Current is increasing, and the voltage across the network, if you will, V sub C, is constant, thus Z is decreasing. And so in the little explanation below, you can see they put some arrows on here showing you that as X sub C decreases, V sub C decreases, but the current increases. Okay, so this is just showing us what the current voltage for the network and the voltage for the capacitor would do as we varied the frequency. So this gives us a phasor representation here of varying the frequency 1, frequency 2, frequency 3, and as the frequency increases, you can see that Z1, Z2, and Z3 varies accordingly. Okay, as the frequency increases then, X sub C decreases, the total impedance for the network decreases, and the phase angle theta decreases. Each value of frequency then can be visualized by forming different impedances. So let's look at a simple RC circuit here where we're going to determine the magnitude of the total impedance and the phase angle for each of the following values of the frequency as it's varied. So in this first case, we're looking at the frequency set at 10,000 hertz, 10 kilohertz. So we start off by calculating our capacitive reactance, 1 over 2 pi FC, and we come up with 1.59 k ohms. Now we work on converting the values from rectangular to polar. So we take the 1 k ohm resistor, square it, now take the 1.59 capacitive reactance, square it, add it together, and we come up with a magnitude of 1.88 k ohms. If we take the negative inverse tangent of 1.59 by 1 k ohms, we get an angle of minus 57.8 degrees. Okay, so that's at 10K. So now let's double that frequency. Let's move it to 20K. So remember these values, 1.59K for the capacitive reactance, 57.8 is our angle. So now at 20 degrees, you can see that our capacitive reactance now has changed from 1.59K to 796 ohms. So it's dropped almost in half. So again, when we calculate our network impedance, we end up with, again, the capacitor stays the same. The reactance for the capacitor has changed, though, and our terms for the negative inverse tangent have changed. So now we have 1.28 kiloohms and an angle of minus 38.5. So 1.88 minus 57.8 versus 1.28 minus 38.5. So now let's increase it to 30K. So now when we increase it to 30K, we see that the capacitive reactance now has dropped again to 531 ohms. And when we calculate our polar impedance for the network, we get a value of 1.13 k ohms and a phase angle of minus 28 degrees K. So you can see as the frequency went up, our values decreased. Okay. So we've looked at different examples in series circuits with series reactance, and then part 2 we'll look at the parallel reactive circuits and how we calculate parallel reactive components.